Yes, thanks for the introduction. Thanks to the organizer for this nice workshop. Today we'll be talking about approximation algorithms for channel coding. This is a joint work with Mario and Marco, and it is based on these two preprints that can be found with these archive numbers. Let me first motivate the problem. So here we are talking about channel coding. So channel coding is the transmission of classical information over a noisy channel. More precisely, we want to transmit a number of messages with a rate R through a certain number of copies of the channel W. In his similar work, Shannon showed that there is a single parameter known as the channel capacity that governs the optimal rate at which the transmission of classical information is possible. It further demarcates a transition point in the following sense. For rates strictly below the channel capacity, it is possible to send classical information with an exponentially small error probability. However, for rates strictly above the channel capacity, there is no hope to transmit information without incurring an error probability that goes to 1 exponentially fast. The channel capacity was generalized to the classical quantum setting, and interestingly, the capacity does not change if the sender and the receiver share random bits or entangled states. So these forms of correlations is particular form of non-signaling assistance, which include any correlations between the sender and the receiver that do not permit communication by itself. Recently, the non-signaling was shown to correspond to the meta-converse, which is a mathematical tool for proving many converses in channel information theory. This is for classical channels, and for quantum channels, there is also the correspondence if we further allow the sender to send a one bit without error. So in this work, we want to study the relationships between these forms of assistance and then explore their implications in terms of high-order refinements. So in other words, we want to show one-shot bounds that are tight enough for high-order refinements in terms of error and strong converse exponents. So our main findings are the following. So first, for classical quantum channels, we show that activated non-signaling strategies can achieve the sphere packing bound. And so the error exponent is characterized for all rates if we allow the sender and the receiver to share, to have non-signaling correlations and to have this ability to send one bit perfectly. The second main finding is that we can round non-signaling strategy to an entanglement strategy, and we have the following approximation in terms of the success probability. And the approximation ratio is only logarithmic in the number of messages and the channel dimension. So before entering into the details of these results, let me recall the channel coding setting. So here the goal is to send a message M through a number of channels and tensor N. In the plain setting, to send a message M, Alice or the sender applies an encoding map E. Then the resultant state is sent through the channel. So in order to decode, so the receiver or Bob performs a measurement. And the success probability is exactly when the outcome is M. Now, in the entanglement-assisted case, the situation is a bit different, and here Alice and Bob are allowed to share some entangled state psi, and depending on the message to be sent, M, Alice performs an encoding map or applies an encoding map to her part of the entanglement, and the resulting state is sent through the channel. Now Bob performs a measurement on his part of the entanglement, and the success occurs when the outcome is M. So in the more general setting of non-signaling, we have this expression for the success probability, and here pi is a super channel that sends channels to channels, and it further should satisfy these conditions. So roughly speaking, the super channel should not allow communication from Alice to Bob and vice versa. So for channel coding, the error or success probabilities are the worst case and average case success probabilities or error probabilities are equivalent. So here we choose to formulate our problem using the average success probability, which is simply the average over success probabilities for any message M. Then the optimal one is just the maximization over strategies in some class A, which can be plain, entanglement assisted, or non-signaling. So similarly, the optimal error probability, which is just 1 minus success, is the infimum over all strategies. Let me first focus on the optimal error probability. So computing the optimal either plain or entanglement assisted error probability is hard. One lower bound is given by the so-called meta-converse. So this is a mathematical tool which implies many converses in channel information theory. The idea is as follows. So in order for channel W to send a number of messages M with an error probability epsilon, the hypothesis test and mutual information should be at least log M. And with this expression, we can define the meta-converse error probability to be the optimal epsilon such that this hypothesis test and mutual information is at least log M. And it turns out that this is a linear program for classical channels. Recently, this meta-converse has shown to be to has an operational interpretation in terms of non-signaling strategies. So the meta-converse corresponds exactly to the setting where the sender and the receiver share non-signaling correlations. So in the quantum setting, the meta-converse is slightly different than the setting of non-signaling, but they become equal if we allow another perfect bit of communication. And this is called activated non-signaling. One application of the meta-converse is for error exponents, the well-known sphere packing bound. So here we are in the regime of rates strictly below the channel capacity. So the error decays exponentially fast, and the decaying rate is known as the error exponent or the reliability function. So for classical quantum channels, the error exponents can be lower bounded by the random coding bound and can be upper bounded by the sphere packing bound. These are very similar bounds. In particular, these are optimization over the same objective, which is weighted and shifted alpha PEDS Renner capacity. The only difference lies in the optimization range. So for the random coding bound, the range is between, the alpha should be between 1/2 and 1, while for sphere packing bound, the range is between 0 and 1. So for rates greater than a threshold, known as the critical rate, the optimal alpha is at least 1/2, and as such, these bounds coincide, and the error exponent is exact. However, for rates strictly below than the critical rate and positive, the error exponent is in general unknown. And this is a long-standing open problem in information theory, even in the classical setting. So in this work, we show that if we allow the sender and the receiver to have activated non-signaling correlation, then we can characterize exactly the error exponent for all rates below and above the critical rate. And this is given by the sphere packing bound. So in other words, we can show that the sphere packing bound is not only a bound on the plane strategies, but also for activated non-signaling or meta-converse. And also we can achieve this bound if we allow the sender and the receiver to share activated non-signaling correlations. Our achievability result can be, okay, before, so this generalizes the result of, classical result of Polyansky, and our achievability result can be generalized to the fully quantum setting. So here we obtain a lower bound on the error exponent in terms of the regularized alpha PEDS Renner capacity. So since the proof is relatively simple, let me describe it here. So the activated non-signaling error probability corresponds to the meta-converse. This is the first equality, and the meta-converse for quantum channels is an SDP. Its dual can be written in a compact form using the non-commutative minimum notation. So this is the expression, and we want an achievability result. So we want to upper bound this meta-converse error probability. So we can use first Odaner et al. Inequality to go from the non-commutative minimum to a geometric mean. Then we can further bound this using Young inequality, and we obtain this weighted alpha PEDS Renner capacity. Now, if you take the optimization inside, this gives this one-shot upper bound on the meta-converse error probability in terms of the alpha pairs Renner capacity. So in the block length, we obtain this upper bound, then we can prove the lower bound on the error exponent in terms of the regularized alpha pairs Renner capacity for fully quantum channels. Now, the fully quantum sphere packing bound is unknown. This is another problem. And if we conjecture that the quantum sphere packing bound should be expressed in terms of the pairs Renner capacity, so this lower bound, this achievability result, suggests that some regularization is needed for the quantum sphere packing bound. Finally, for classical quantum channels, the alpha capacity is additive, and we can prove in a similar way the sphere packing bound, so we have this tight characterization of the error exponents for all rates. Now that we have focused on the optimal error probability, let's turn our attention to the optimal success probability and recall that the success probability is just 1 minus error probability, but this is a quite different metric. So let's start with this nice result of Bergman and Fawzi. So here they showed that the non-signaling success probability can approximate the plane success probability for classical channels, and the approximation ratio is given by a constant 1 minus 1 over E. Since this is a constant, it has implications in terms of the strong converse exponent. So here we are in the regime where the rate is strictly above the channel capacity. So the error goes to 1 exponentially fast, so the success goes to 0 exponentially fast, and the decaying rate is known as the strong converse exponent. So this inequality or approximation of Bergman and Fawzi implies that the strong converse exponent of the plane and non-signaling are equal, and so any correlation in between. And recall that the non-signaling in the classical setting corresponds exactly to the meta-converse. So you have this chain of equalities. Now, for fully quantum channels, we have seen that meta-converse is different than non-signaling, and we can see more precisely the difference here in their respective STPs. So they are comparable, but the only difference is that the constraint on lambda b should be at most identity for the meta-converse, and it should be equal to identity for the non-signaling. And it turns out that in terms of the success probability, we can round a meta-converse to a non-signaling, and the approximation ratio goes to 1 when m goes to infinity. So this is already enough to generalize our previous equality between the non-signaling and meta-converse, strong converse exponents to fully quantum channels. And this is important because the meta-converse corresponds to the hypothesis testing. So we can use existing results of hypothesis testing to characterize the strong converse exponent for the meta-converse. And it is given by this optimization of weighted and shifted sandwiched alpha capacity of order greater than 1. Now we can ask about the entanglement assisted. So here we start with the quantum classical channels. So we can further round a non-signaling strategy to an entanglement assisted strategy, and we can achieve this tight constant 1 minus 1 over E. So this allows us to translate our previous equality to the entanglement assisted setting. And here I would like to emphasize that we have this one-shot approximation that is tight enough for the strong converse exponent. Now, for fully quantum channels, we are unable to prove this 1 minus 1 over E approximation ratio, but nevertheless, we can give a rounding result for fully quantum channels. But before this, let me define V to be the number of distinct eigenvalues of ρr, which is a state, optimal state in the non-signaling success probability semi-definite program. Now, for any quantum channel, we can round a non-signaling strategy to an entanglement-assisted strategy, and the multiplicative error is only polynomial in this number of distinct eigenvalues and logarithmic in the number of messages and the channel dimensions. Using symmetry arguments and the post-selection technique, we can show that in the block length, this approximation ratio is only polynomial in n. And so this is enough to have this equality between the non-signaling and entanglement-assisted strong converse exponents. So this gives an alternative proof of the entanglement-assisted strong converse exponent, initially proved by Li and Yao. And further, here we show that non-signaling cannot help to improve the strong converse exponent. So in the remaining time, I would like to give a sketch of the proof of this rounding result. The first inequality is trivial because non-signaling subsumes entanglement-assisted, and we want to prove the second inequality. So for this, we can choose an optimal solution of the non-signaling semi-definite program and design an entanglement-assisted strategy, achieving this inequality. So in the SDP of the non-signaling success probability, we have two objects, rho r and lambda. Rho r is a state, and lambda can be turned to an observable by dividing with m rho r. Now, this state and this observable have some relations. So first, we can purify the state rho r to phi, and if we measure the output state under the channel n of the purification with the measurement given by the O and I minus O, then we can observe the first outcome exactly with the success probability non-signaling. But if we measure any product state with the first marginal being rho r, the probability of observing the first outcome is 1 over m. Now, this is the only information we have, and we want to design entanglement-assisted strategy. So we can first use the position-based and sequential decoding. So here, the shared entanglement is m copies of this purification of rho r. So in order to encode a message m, so Alice swaps the system AM with her system and then sends the system with the channel N. So in other words, the message M is encoded in the mth position of the shared entanglement. Now, Bob, or the decoder, does not know this position. So in order to find the position, he sequentially measures any system of the shared entanglement as well as the system he received by the channel using this observables O for different positions. And once he observes the first outcome, he stops and returns this position. Now, in the quantum classical setting, the analysis is quite easy, and we can show this lower bound on the ratio of the success probabilities, and it is given by exactly this constant 1 minus 1 over E. However, for fully quantum channels, the observables for different positions do not commute, and the analysis is quite hard. So our first attempt to overcome this difficulty is to use the well-known Hayashi-Nagaoka decoder and inequality. So here we take the observables and we divide them by the sum. We can achieve this approximation which has an additive error that scales like square root m prime over m. So this is good enough for second order, but not for strong converse exponent. So our second attempt is to follow this work of Fawzi et al. So here, instead of normalizing by the sum of the operators, we normalize by the operator norm of the sum, which ensures that this is a valid PUVM. And furthermore, this normalization lambda will appear as the approximation error, and it is multiplicative in terms of the success probability. Now, to bound this approximation error lambda, we can use the metric Chernoff inequality, and this idea was already used in this Fawzi et al. Work. However, in the fully quantum setting, the only information we have about O is this second constraint we have from the SDP, which is quite different than the hypothesis of the matrix Chernoff inequality. So here the naive bound is just to use the fact that O is an observable and then upper bound this operator norm of the sum by M, which is not good enough to have this concentration here. So for this, we will focus on this constraint, which can be turned to a constraint in the partial trace, And then we can further simplify our problem by taking rho to be the maximally mixed state. Now the constraint is just the partial trace on the observable, and we are a bit close. So we want to turn this partial trace on expectation, and for this we can conjugate by a random unitary. So any one design can give us this identity, so we conjugate the system a random unitary on the system R with any one design or R random unitary. Now this constraint implies that the operator norm of the expectation is at most 1 over M, and this is very similar to the assumption of the matrix of inequality. And this suggests to conjugate any observable by a random unitary, and instead of this naive M, upper bound M, now we obtain an upper bound 1, which is better and gives that concentration. But we need to change the protocol so that we have this random unitaries. So in our decoding, we can add this U random. Then in the non-significant success probability, we need also to add this U. And recall that the maximum mixed state is our assumption of the rho R to be the maximum mixed state. So the purification is actually the maximum entangled state. And the maximum entangled state has this property that we can turn a conjugation of unitary on one system to a conjugation of its transpose on the other system. So now this action can be viewed in the Alice's side. So Alice can conjugate using the unitary before transmitting the system. And it turns out we don't need the positions. Only one entangled state is sufficient. And now this is fine. We can use the concentration of the matrix of inequality. We have this lower bound on the lambda, which is only logarithmic in the number of messages and the dimension. However, we have this assumption on the maximally of rho R being the maximum mixed state, which we cannot ensure always. So the last ingredient is to use this input flattening technique from Li and Yao. So here the idea is to see the optimal input state rho R as a convex combination of maximum mixed state over orthogonal Hilbert spaces. Then we will use shared randomness. We will pick some J from this distribution P, and then if we have some sample J, we can work as if we have a maximum mixed state on the Hilbert space as Hj. So this is the scheme, and so here we get this V. So because of the Pinch inequality, and matrix of inequality is also gives us this nice concentration, and only we pick this additional 1 over V squared. So you can find the full details in the preprint. Now to sum up, we have seen that the non-signaling and meta-converse are two useful organizations. They provide efficiently computable bounds, one-shot bounds on the error and success probabilities. And these one-shot bounds can be further used to characterize high-order refinements. I would like to end with an interesting open question. So channel coding is a special case of the channel interconversion problem, where we aim to simulate a possibly noisy channel T using another possibly noisy channel W. The other extreme, where the initial channel is identity, is known as channel simulation, and we have seen the talk of Michael Monday, where this meta-converse was also used and was also shown to be tight enough to give error exponents and strong converse exponents. So the first order of channel interconversion is given by the ratio of the channel capacities, but nothing is known beyond that. So recently we have explored the strong converse exponent in the classical quantum setting under the worst case purified distance, as well as the strong converse exponents in the classical setting under the worst case total variation distance, together with the Yongshan and Mario. This work will appear soon. But there are many other settings that remain open here. Also for error exponents, nothing is known, and we expect to have some critical rate there because of channel coding special case. And finally, the small deviation, also known as second order, is also an interesting open problem. So with that, I would like to thank you for your attention.
Okay, thanks, Aadil. Questions? Okay, maybe a very short question. So can you say, so what is the technical difficulty if you want to go to error exponents, even in a restricted setting, that it doesn't work? Is this easy to explain?
Which problem?
Sorry? I mean, you pick one you want to have, for example, non-signaling or something. Or if you say error exponents here, what can you comment a bit on this? The open question.
Oh, on the open question. Okay, for the channel interconversion.
Yes. Sorry, this is only for channel interconversion.
Interconversion.
Sorry.
Yes, the critical rate for channel coding is, this is a long-standing open problem. Yes. So the difficulty to go to for error exponents for channel interconversion, I think there is always this concatenation strategy that you can go from W to identity, then you go from identity to T. However, this concatenation strategy is not always optimal. And so I'm not sure if one can get like the tight error exponents, but you always can get a bounce using this strategy. So for the converse, we need to generalize this notion of the meta converse to channel interconversion. And usually, if one of them, W or T, is identity, you have some structure and you can use symmetry arguments. Now, if you have general W and T, we lose this structure and we don't have any more this symmetry reduction. I think this is the difficulty for the converse.
Okay, thanks. So last chance for question. Otherwise, let's thank Aadil again. Let's continue.